I'm going to go ahead and introduce the next group. Our next group presenting is called the GCC Pottery Wheel. This group was advised by Dr. Ulrich. So if the first presenter could go ahead and activate your video, make sure that each of you introduce yourselves as you switch from one person to the next. You may go ahead and start your presentation.
All right. Hello, everybody. My name is Laura Reiner. I'm the spring team leader of this project. I am a member of the frame and centering device sub-teams, and today I will be introducing the Pottery Wheel project to everyone. So to begin, we discovered a need at Grove City High School's art department. This department is very inclusive because they help students with disabilities learn to create art and therefore increase their independence. However, the current wheelchair accessible pottery wheel by Brent that the school had possessed several problems. So the first problem was that the splash guard, which is the yellow guard surrounding the wheel, was very high, and this decreases a student's mechanical advantage when they lean in to create pottery. Additionally, another problem with that splash guard is that the rim is very hard, and for those with sensory issues, this can create problems. Another problem is that some wheelchair models had a hard time fitting under the table, even when the table was adjusted to its highest position. Additionally, the armrests, which are shown off to the side, are very difficult for a student to reach, so they just got in the way of aids that were trying to help the students. Another problem is that the speed control for the wheel is done with a foot pedal, which is just impractical for those in wheelchairs. And the foot pedal, which is mounted off to the side of the wheel, is very hard for a student to reach. And even if they can reach it, it's generally hard to use because it's jerky and awkward. So one final problem is that the height of the table is difficult to adjust with the hand crank, and this is because clay and water make their way into the crankshaft, making the handle hard to turn. So to address these problems, we came up with some design goals. So the first goal is to decrease the height distance between the belt guard and the top of the splash guard. So this will help a student increase their mechanical advantage when making pottery. Another goal is to increase the comfort and usability of the armrests. We also want to increase a student's independence in turning the wheel on and off and controlling its speed. We want to ensure easy cleanup for a student or a teacher. We want to ensure all foreseeable wheelchair models can fit comfortably under the table. We want to ensure easy and safe vertical adjustment of the table. And of course, we want to accomplish all of these goals for under $3,000. So to give you an idea of our final design, I've included a Creo model of our final assembly. Unfortunately, we were not able to finish manufacturing our pottery wheel, but we do believe that our final design accomplishes all of our design goals. So to talk about our design in more detail, I'm now going to pass it off to Alec.
Hi, I'm Alec Gaiman, and I was also a member of the frame sub-team and was in charge of the ergonomics for our project this year. The frame subassembly is made up of two main parts, the first being the lift, which supports the table itself and allows the students to change the height of the table, and the second being the base, which is shown in the upper right image on this slide. First, going into detail about the base. The base is the main support component of the entire assembly, and the tubing was made of a steel that we had custom bent with the 6-inch radius at a nearby muffler shop. Also, as you can see in that image, there are 4 steel plates with holes that match up to swiveling casters that we purchased. The casters have rubber wheels with brakes on each wheel so that the assembly can be easily moved around and locked into place during the student's use. The rubber wheels also prevent a lot of marking on the school's floor. The motor for our design is the same one used by Brent in their Model B pottery wheel and will be mounted to the component that is seen in the bottom right-hand image, the table support. The top of this support is welded to the back of the table and to the back of the lift. The table support also has mounting holes, which you can see on the left side of the part that allow for the shaft to pass through the part and attach to the wheel head. The motor is going to be mounted on the inside of this table support where those slots are that you can see below. And we chose to include slots instead of holes for the mounting so that the motor can be moved and adjusted side to side, which is our method of belt tensioning. Next, I'm going to be going into the lift, which is the second main component of the frame. And the lift is just that vertical component of the frame responsible for adjusting the height and where the table is going to be attached to using the table support that I mentioned earlier. Anthony Polizza was the main designer of the lift, and we're in the process of manufacturing most of these parts in the Grove City shop. The lift has a two-stage design. The upper tubing, which cases the assembly and supports the carriage and the rollers, and the second being the lower tubing, which supports the railing systems. Both of these tubings were made of steel, and we already had cut them to size in the shop. As you can see in the bottom right-hand image, both of those tubings are included, along with the bent tubing that is part of the base that I mentioned in the previous slide. The motor for the lift was going to be mounted on the top of the upper tubing on an aluminum cap that was also being machined in the Grove City shop. And this lift motor was ordered as a single-speed maker motor with a worm drive that added some safety for the students. The rollers inside of the tubing tracked on side-mounted railings for the linear movement of the table and the pottery wheel, which was converted from the original rotational movement of the motor by a lead screw throughout the lift. The final lift assembly would have allowed very easy and safe adjustment of the height of the table by the students independently or by their aides if needed. So next, I'm going to be passing it off to Freddie Raup, who's going to go into detail about the armrest assembly and the table.
So, hi, my name is Freddie Raup. I was on the armrest and wheelhead sub-team, and I'll be explaining the design and manufacturing of the armrest, ergonomics, and wheelhead. For the armrest on the original Brent pottery wheel, students were resting their arms on the splash cover, which was a narrow bent piece of plastic. This hurt their arms, was too high, and had to be removed by the aides for cleanup. So in our design, we made the splash cover and table into a single piece. This allowed us to reduce the overall height, widen the surface area used as an armrest, and would make cleanup much simpler. We also were able to add a 1-inch rim all the way around the table to make it easier for the instructors or aides to help the students. This combination also reduced our cost and part count, as well as gave us a secure surface to attach to the lift and mount the centering device to. The part itself was made out of a 3/16 stainless steel sheet that was then bent and welded. It was thick enough to prevent deflection, even if the armrest was sat on by a large person. Additionally, we chose stainless because this part would be very regularly exposed to water or even standing water, and we didn't want to have any risk of corrosion or damage. And then we outsourced the fabrication of this to a company called Laser Fab out of Lebanon, Pennsylvania. For the ergonomics, Alec designed a piece of vinyl wrapped 1-inch foam to mount directly onto the armrest. This was especially critical as making pottery is very reliant on keeping your arms tightly in place. So the student would be pushing forcibly down on the armrest to keep everything tight. So between enlarging the armrest and wrapping it in foam, we were able to ensure it would be a comfortable experience for the user and still be easy to clean up. Additionally, we were going to add a 3/16-inch rubber guarding around all the exposed edges of the table. This was especially significant for the aides, as they would be approaching the wheel from the side to assist the student, and they could be leaning on those 1-inch edges for short periods, and we didn't want them to get cut or scratched when doing so. And now for the wheel head, part of merging that removable splash cover with the table meant we needed a way to clean up underneath the wheel head from time to time. To do this, we designed this quick detaching system, and with that design, it had to stay in place while spinning and not accidentally release, but also still be easy to remove when doing so intentionally. To accomplish this, we designed a spring tensioning system. This system had the wheel head with a coupling mounted onto it. That coupling had an L-shaped slot that a shaft and pin assembly would fit into, and then would all be held in place by the spring tension. The rotation of the wheel would also help keep the pin in place. And then all of this was held in place by 2 collars on opposite sides of the table, as well as a system of bearings. Then we had hoped that we would encase this whole assembly in a thin piece of plastic guarding that would decrease any chance of water getting into it, as well as eliminate any risk of pinch points. Though few of the components were actually manufactured, the only one was shown up there on the right would have been the coupling, but we're optimistic that it would have worked pretty well for us. So from here, Maddie will be discussing the electronics component of our project.
Ready. My name is Madison McKivergan, and I was a part of the electronics sub-team for the Special Needs Pottery Wheel project. I was also the fall team project leader. So the electronics team tackled two main problems in our design, mainly creating an accessible speed control mechanism, and then wiring the entire wheel to ensure safe distribution and flow of power to every electrically operated sub-mechanism. Beginning with the speed control device, several different options were explored, before settling on a hand-operated lever attached to the side of the wheel with magnets to allow for easy access to the student. Using the 8.5 by 3.2 by 2.2 inch 3D printed box with mechanical stops for the slider, we attached a printed S-shaped lever that protruded out of the bottom of the box towards the student. The box also included one of two kill switches in our design, a waterproof on-off button located in the front of the box to let the student turn on the wheel independently, yet it was only wired to work if the main control box was working as an added safety measure. The first printing of the box and associated lid and lever in onyx material went very well, and almost all dimensional tolerances were acceptable. The metal dowel system designed to hold the lever in the box smoothly and kept the lever in place. Additionally, the potentiometer fit well into its compartment, and the waterproofing measures appeared to be adequate. However, small details did become problematic. Holes didn't line up with each other, the lid needed to be remodeled to fit around the outside of the box for additional waterproofing, and the opening of the kill switch needed to be switched from the side of the box to the front in order to allow for more space. These items were addressed in the remodel, but unfortunately were never 3D printed again because of time constraints for COVID-19. Hopefully, future teams will be able to build and use this size. So moving on to our electrical circuit, the wiring circuit was supposed to be very simple overall, but unfortunately became more difficult once it was realized the control box we bought was very different from the control box we designed off of. Basically, the control box that we bought did not have connections for outputs to the potentiometer and kill switch that we were looking for. A detailed was never created because of the virus, but as shown, the current from the wall would power the Brent Classic Controller B, which we plan to adapt, and the controller would connect to the linear potentiometer and two kill switches. One on the box for the student to turn the wheel on, and one located near the controller for the aid to use if necessary. The potentiometer then directly controlled the flow of 0 to 115 volts of current into the wheel motor. The lift motor plugged into the wall separately using a power adapter. Though never finished, this design is fairly simple and should be able to be followed or easily adapted by any future teams, as long as the control box is modified in order to allow for additional output. Now I will hand off to Cassie to talk about our center.
Thanks, Maddie. Hi, my name is Cassie Shakluna, and I was part of the armrest sub-team that Freddie had talked about earlier, and I was also part of the centering device sub-team, which I will now go into detail about. In addition to all the other design components, we decided to create an accessory to this pottery wheel. As we observed the students at Grove City High School, and just from simply talking to some people that are more familiar with pottery, centering the clay on the wheel is arguably the hardest part of throwing. So to help students overcome this challenge, we created this device, allowing them to throw more independently. With many different centering devices out there, all for a very steep price, we decided to create our own in-house. Our design is based off a strong arm tool and includes not only a centering tool, but an opening tool as well. This will then aid the students in opening their clay directly in the center. During our research phase, we did check for any patents on the strong arm centering tool, and there weren't any, so thankfully this allowed us to move forward with our modified design. So to save costs but still be efficient in our design, we used PVC for the handles, aluminum plates were used for both the base and the centering device, and a wooden block was used as a separator between the PVC, and we were able to use some materials found in the shop in order to reduce this price even further. This device is dual functioning in that one arm is designated for centering the clay and the other arm for opening the clay. Mounting holes were drilled into the mounting plate for easy attachment to the table, but this would then also allow the device to be detached and maybe used on other pottery wheels. For centering the clay, a plate would be attached to the bottom PVC arm and then pulled against the unformed clay for the student to have assistance in the centering process. For opening the clay, an aluminum rod would be mounted to the upper PVC arm. The smaller diameter on this rod is externally threaded for vertical adjustment via the mounting bolts. To use the opening device, it has to be brought down, resting on the top of the ball of clay, directly in the center to then open the piece. But the height can also be adjusted on this device so the rod does not rip through the bottom of the clay. While we were very close to completing the final product, unfortunately we had to leave campus and leave this product behind. As you can see in the images to the right, the base plate and rod were completed, as well as the opening device, and the PVC was cut to the appropriate length. Though we were not able to fully complete this design, we are hopeful it will be complete in future years. And I will now pass it off to Jacob Sheila to talk about the safety considerations for this pottery wheel.
All right, thanks, Cassie. My name is Jacob Sheila, and I'm going to talk a little bit about the safety that we used in this pottery wheel. I was also part of the centering device team and the electronic sub team. When we first started off to create the pottery wheel, we wanted to make something that was going to be safe for the students to use, and we looked at the safety checklist that Grove City College had given us to make sure we checked off as many of the boxes as possible. The first thing that we did specifically to help with our safety is with the lift. We wanted to make sure that the lift wasn't going to move up too fast, up or down too fast, in order to protect people from legs getting pinched or fingers getting pinched, especially with students using wheelchairs and armrests that might be sitting underneath it for fingers to get pinched between. The next thing we did was we looked at the electronics and the emergency stop buttons that we added. Our emergency stop button was a two-button stop function, which we wired 2 buttons in series, and this allowed for that if either button was to be pushed, the machine would be stopped. The first button would be an emergency stop button that would be connected from the wall before it got into the model control B, and this button would be mounted somewhere that the aides would be easily able to access. This one would be more of an emergency stop button, and anytime, if at any time the aides decided they needed to stop the machine, they'd know where this button is and it wouldn't be moved. The second of the button would be the power on-off button that would be mounted on the speed control. This would be able to be moved for any of the users' accommodations so that they were able to use it in any location that'd be easiest for them to hit in case something were to go wrong. This two stop button function was wired, as I said earlier, wired in series so that if either aide or the student needed to stop it, it would stop with only one of the buttons being pressed. The other thing we did the electronics is we wanted to make sure all the electronics were covered. That way no water could get in and damage electronics, or people could get access to them to electrocute themselves or mess with anything. So we completely covered all the electronics with the electronic box that we made, we 3D printed, after we would have put the lid on. The image you saw had the lid off so that you could see the electronics going on. The next thing we looked at was the base of the actual table. We wanted to make sure that this base was wide enough in order to allow it so that it wouldn't get knocked over if somebody bumped into it or while they were trying to move it. We also, as talked about earlier, wanted to make sure that if somebody were to lean on it or if an aide were helping and were leaning on the table, it wouldn't collapse under the weight. So we made sure it was able to withstand the weight of a person leaning on it. And the other thing we did with the base is we put wheels on it in order for it to be easier to move so that nobody strained themselves and the table wouldn't tip over if they had to actually physically move the machine altogether. We also wanted to make sure that the wheel head would be quick to attach so that we could clean it easily. And as we talked about earlier, we was able to then put the plastic covering over top all the small components so that nobody could pinch their fingers or get their hands into anywhere that might cause them to get pinched or crushed. Lastly, we wanted to make sure we put a rubber edge on the edge of the corners so that if the aides were leaning over to help, they wouldn't get cut or scraped, and they were also comfortable as they were leaning over to help. And also in case anybody were to fall or bump into the machine, they wouldn't get cut or scraped. Next, I'm going to hand it off to Anthony Polizza to talk about the economics of our machine.
Thanks, Jake. Hello, everyone. I'm Anthony Polizza. While a member of both the frame and electronic subteams this year, I was also tasked with compiling our project expenses to illustrate our financial budget. For our financial report, I broke apart our expenses into 9 groups. 7 of those groups follow along the subgroups that we worked in over the course of the semester. The additional 2 are combined for the Brent purchased belt drive and a miscellaneous group that contains some odds and ends parts that don't fit in. As Laura mentioned at the beginning of the presentation, our project budget was $3,000. And our PDS goal was to stay under budget, to conserve funds for 1, but 2, to also remain competitive with industry standard pottery wheels made by Brent or Amico. Our total project cost came to $2,641, and the 3 largest groups were the lift, electronics, and the armrest. Those groups combined for 76% of our total project cost. Adding in the Brent purchased parts for the belt drive increased that percentage to 92%. With 3 or 4 of our 9 main groups costing more than 80% of our total project cost, our project did not follow the Pareto principle of 80-20. The future steps for our project, had we had time to complete it, were 1, to finish our specialized parts that were being finished in the GCC machine shop or by one of our team members. Those parts included the top and bottom caps for the lift assembly, as well as some small parts for the armrest and wheel head. After those parts were finished, we wanted to start assembling our project and begin testing the pottery wheel as a whole unit. We were very excited about this step because we believed we had enough time to accomplish testing, but before we were not be able to accomplish that by the time we were sent home. Once testing was complete, we wanted to increase the aesthetic of the total project. Some of our ideas for this were to add colorful paints and include some student designs such as handprint paints and student signatures. Once completed, the project was then to be relocated back to the Grove City High School. There was also one area of our project that we believed a future engineering project could expand upon. The students that will primarily be using the pottery wheel at the high school already use personal tablets that have eye tracking software that allows them to communicate with their aides and advisors. This Tobii eye control software can be implemented with other electronics using a specified controller. A future team could then program controls and buttons for students to use on their personal tablets that would work with the specialized controller implemented with our pottery wheel electronics to control the speed of the pottery wheel. That is the end of our presentation. Does anybody have any questions?
Hello, this is Brian Montgomery. Can everybody hear me?
Yes.
Okay. Just a quick question. So I was noticing on the Brent wheel, you guys moved from the, looks like just from wheels and sort of like a screw down foot, you went to a caster with a locking foot. Can you explain that? Was it just for a consolidated design, or is that just something you decided to integrate together?
Yeah, I can answer that. So originally we did, actually after the first semester, we did still have the design with those feet. And then right before we purchased them, we decided just to switch it and consolidate it with the brakes. And we also did leave room in our design if once we tested it, if we had gotten the chance to test it, that if we didn't really like the brake design, we were going to be, it would have been very easy to implement the stands. So we left that as an option, but wanted to consolidate it and save some money there originally.
No, that's good, because in some of the equipment I've seen, you usually end up with those feet just for stability. If you're going to lean against it, sometimes the locking casters don't make it quite as stable. But that's good that you guys integrated both options for the future. Good presentation. Thanks, guys.
Thank you.
I have a question. So
Go ahead.
I was curious as to why you guys had decided to 3D print the box for your guys' electronics rather than try and find something else to use, because sometimes, especially with a box that size, it can get kind of pricey for 3D printing.
So yeah, that's a very good question. I would say that yes, the fact that we had the 3D printer available to us and we had the budget in order to use it definitely was one of the main reasons we decided to do that versus using a different sort of box. But we did look extensively to find boxes that we would be able to use without too much trouble. And the problem is we were looking for something very specific because it needed to be light and small enough to adhere via magnets to the side of the wheel. And we also needed special mechanical stops to keep the linear potentiometer from breaking because it was very, very fragile. And we also needed the ability to mount the potentiometer indirectly. So basically we needed an extra edge that we weren't going to be able to find in a commercial box. So those are all some of the reasons that we just decided it would be easier to 3D print the box versus kind of higher.
So maybe to add to that, Brent had mentioned to us last semester that they were potentially interested in our design. So I feel like if you ever took this to like a full-scale production level, you could maybe convert that box to injection molding or something like that. I think the 3D printing is a good way to get an initial design on that box.
Any further questions from anybody in the audience?
I just want to put my 2 cents worth in and say good job.
Great. Thank you, Dr. Ulrich. All right. So thank you very much.